Welcome to the session on verification and secure systems. So we're going to have three speakers in this. So Ed Nightingale is going to talk about Azure Sphere and secure hardware. And then Adam Chapala from MIT is going to be talking about formal methods and how that drives system design. And then finally, Nick Swamy from MSR Labs is going to be talking about the Everest project and verifying TLS. So let me go ahead and turn it over to Ed.
Thanks, Chris. You guys hear me? Good morning. It's my pleasure to be here. My name is Ed Nightingale. I'm one of the members of the Azure Sphere team. This is a product that was just announced this spring. This talk might be at a bit of a different altitude than I might normally give at a faculty summit. We're really looking for some engagement with the academic community, some feedback, and I'd love to talk to you all later in the day. So, and actually, right now, you can order a development kit if you're interested in playing with the Azure Sphere product or trying to hack it. We'd love that. So what's Azure Sphere focused on? Azure Sphere is focused all around microcontrollers. Microcontrollers are low-cost, single-chip computers. Microcontrollers are really in all of the devices around you, in your home, in your hotel room, at work, that you never think about. There are 9 billion MCU-based devices built and deployed every year, more than one per person on the planet. And if it has a screen, if it has a button or a low-res screen, it's got a microcontroller in it. Now, what's the big change? About 4 years ago, you started to see microcontrollers with a radio. And this is, in the cost of around, a chip like this is around $2.50. So if you said, well, for $2.50, I can take those 9 billion devices and connect them all to the internet, I think for most of those devices, you say, obviously, we should connect them. It enables us to produce new experiences, enables us to interact with them live, and to kind of have new connections with the people who are using those devices. Now, the interesting issue is that only about 1% of these MCU devices are connected right now. So why is that? Well, you have this huge opportunity in connectivity, and you also have a large amount of risk. We'll just go to this simple example. I think everyone in this room has used a refrigerator or has one. And the simple example for connectivity is, how do you know whether the compressor has failed in your refrigerator? Well, without connectivity, you wake up in the morning, you've got melted ice cream all over the floor. With connectivity and predictive maintenance, you might get a phone call from your device manufacturer, and they say, you know what? We've noticed your compressor is starting to fail. Can we stop by and replace it? Obviously, that's a better experience than the one with the melted ice cream. But what happens when you connect a device to the internet? Well, we all know what happens when you connect a device to the internet. We've seen all of the stories. You've seen baby monitors that are turned into spying devices. You've seen refrigerators that are sending spam. We're seeing ransomware attacks. We're seeing hackers infect millions of devices all over the world. I saw something the other day. I actually took my router and threw it in the trash because the FBI said that's what I should do with it because they couldn't update the software remotely. Never done that before. We're in a space where we have this huge opportunity for low-cost connectivity, and we have this massive amount of risk. And a really good example of this is the Mirai Botnet from 2016. The Mirai Botnet, these are just simple IP cameras, and it took down basically the internet on the east coast of the United States. Now, what's scary about the Mirai Botnet? It's only 100,000 devices. It's a tiny number of devices. If you look at one market for connectivity, like major appliances, there are about 350 million major appliances sold every year around the world. 100,000 devices can take down a portion of the internet's infrastructure. Imagine 1 billion refrigerators that have all decided to DDoS. The other sad thing about this attack, there's well-known weakness. I believe it was a fixed password. The password was shockingly ROOT. You couldn't change the password. And even worse, once they saw the exploit happening, there was no way to update the software on it to get rid of it. It was just a mini disaster. Another great example recently is that there is a connected thermometer in a fish tank. Someone was able to hack it, and they were able to actually use this to bounce over and attack a database and get access to high-roller data. So, we're in the Wild West. We're in a space with IoT where security is an afterthought. What are we going to do? Well, the first thing we're going to do is, when we talk about connectivity for major manufacturers, is, I'm going to beat this dead horse. Imagine that refrigerator. You wake up in the morning, but instead of melted ice cream, you've got a text message on your phone. It says, we've pawned your fridge. Send us Bitcoin, or all your ice cream melts. The more important one, I think, is, you wake up in the morning and 500,000 stoves have blown up. There's actually a customer we spoke with who had a stove that was in development, and they did a security audit after we talked to them. They figured out that through a software exploit, they could turn on the gas in the stove, and an arbitrary amount of time later, they could light it. So that did not hit the market, thankfully. They caught that, but the risks are really real. The risks are about physical harm. This is foundational. I think everyone in this room knows that security is foundational, and I think the issue is really trying to create platforms where security comes from first principles. So what's Microsoft doing about this? What is Sphere all about? Well, there's two things we want to talk about. One is a set of co-authors and I authored a white paper called The 7 Properties of Highly Secure Devices. These properties are measurable. Now, why do we do this? Well, we felt that there was no bar someone could look at when they were looking at an IoT solution and determine the level of security that it had. Everyone simply says, you're secure. It's black and white. It's a single bit. Everyone in this room knows that's not how security works. This is us putting a line out there, a marker that says this is the minimum bar any device that's connected to the internet should meet to have the potential to be secured. So you have a lot of basics here, right? You have a hard root of trust. We have things like defense in depth, keeping your trusted computer base small, certificate-based authentication, failure reporting, and readable security. So this is up on the web at aka.ms7 properties. We'd love for you guys to read it. We'd love feedback about it and have a conversation about these 7 properties, what those properties provide, and why do you think we've hit the mark there, or you think that there's room for more discussion and engagement here. One of the most important things, though, is that someone who's not a security expert, at the very least, could take these 7 properties and just ask, do I have the 7 properties? Do I have a hard root of trust in my device? Do I have certificate-based authentication? And if they don't, they can start to ask, why not? So that's properties. I want to talk in detail about a couple of them. Some of these properties only depend on hardware support, and this is where we're going to get into the need for secured silicon in addition to software and services. Classic examples are hard root of trust. It's not a forgeable cryptographic key, protects the hardware's identity so it can't be spoofed, and implements hardware for things like secure boot, so we guarantee that only signed software runs in a device, and you eliminate the possibility of random malware being loaded and executed. Some properties depend upon hardware and software. So an example here is a dynamic compartment. Dynamic compartment you can think of as your MMU that provides address space translation and process-based isolation in an operating system. So dynamic compartments mean these compartments can change on the fly. You can update them and change them later, and provides a protection from one process, as an example, not being able to take down another one. So last, some of these properties depend upon hardware, software, and the cloud. So as an example here, we think about renewable security. What does that mean? It simply means that we know attacks are going to happen. We know exploits can be found. Does an IoT device have the ability to update its software remotely and securely? And this requires cloud to provide the updates, software to apply that update, and hardware to prevent rollback attacks. What's a rollback attack? A rollback attack is a really clever attack where you have an old version of, let's say, signed and legitimate software that has a known vulnerability, and you trick the device into basically downgrading to a legitimate but buggy version of the software so you can exploit it. You have to have support in your hardware root of trust, for example, in eFuses, to be able to prevent rollback attacks from occurring. So those are the properties. What's the product? What did we announce? Azure Sphere is an end-to-end solution that's composed of 3 pillars. We have Azure Sphere, we're calling certified MCUs. I'm going to give you a deep dive of what a certified MCU means, what properties those MCUs have, an operating system, and a set of security services. So the certified MCU is provided by Silicon Partners with built-in Microsoft security technology, provides connectivity, and guarantees a dependable hardware root of trust. The operating system is secured by Microsoft. We guarantee we're going to provide updates for at least 10 years, and it provides a trustworthy platform for IoT experiences. And the security service. The security service brokers trust between devices and the cloud, looks for emerging threats through failure reporting, and allows for renewable security. I'll talk about that brokering trust in a little bit. So let's get into what an Azure Sphere certified MCU is. We could use the term crossover MCU in this slide. All these Azure Sphere MCUs are connected, so they have built-in networking. They're secured with this built-in security technology, which we call Pluton. and it's a crossover. And what does that mean? When you look at a typical MCU, if you're in this space, you're talking about something like a Cortex-M. Cortex-M has physical addressing. It lacks a lot of the properties we're looking for. Across our MCU, we have both a Cortex-M and a Cortex-A. A Cortex-A gives us address translation, lets us run a higher level operating system based on something like the Linux kernel, has SRAM and flash, and is protected by a bunch of what we're calling silicon countermeasures that help guard against software that ends up being exploited. So Pluton is the hardware to trust. What does it do? It guarantees the authenticity of your software, so it implements secure boot through ECDSA. It protects against downgrade attacks, so it has the ability to, through fuses, protect against an old but buggy version of software ever being run on the device. Protects the authenticity of the device itself, so it has its own cryptographically based identity, which means you can always tell when the device connects whether it is who it says it is. It reduces supply chain risk. What do I mean by this? There's a great story you guys can look up out there of a certain model of phone that one of the warehouses was physically attacked, and they rooted 52 models of phone and put malware on it. So when these phones arrived at businesses, they came out of the box with the cameras on and the microphones recording. So having secure boot, guaranteeing that every piece of software is signed, eliminating the ability to have something like a rooted or development mode that someone can arbitrarily turn on, eliminates that type of risk. The Pluton and Azure Sphere MCUs are known about from the time they're birthed at the silicon manufacturer. So as that chip comes out of the foundry, we know about its identity, we register that chip, and then we can basically know about the chip throughout its lifetime, which means we can tell what an authentic chip is and what isn't. Now, it accelerates common cryptographic tasks like ECC and AES. Protects against low entropy attacks, so Pluton is a true random number generator. It measures its own entropy. So it looks, for example, if you cool the chip down to try to reduce the space in which it's generating random numbers, it actually shuts itself off. So that's all about Pluton. Those are the guarantees that it provides. A little bit more detail for this audience. It has a dedicated core and its own TCM memory that resists side channel attacks that focus on a single core. This true random number generator. And it also implements remote boot, measured boot and remote attestation in silicon. So it uses a digest accumulator register and a nonce register to allow us to implement remote attestation with our services and look at what software is actually running on the device. So why do we have Cortex-A? I get this question a lot from folks who are in the MCU space. Cortex-A is typically a bit bigger in area. You should end up using a little bit more memory if you're running an OS on there. When we think about security, portability, and extensibility here. So security, basically, because we get isolation. Cortex-M chips don't have MMUs. They don't have address space translation. Having Cortex-A allows you to have process-based isolation and what we call this, meeting the 7 properties for dynamic compartmentalization. Also has a special operating system. I'll get into the details in a little bit. So the OS includes our own runtime and a custom Linux kernel that's been focused on the IoT space. So as an example, we talked about those default passwords. The Azure Sphere operating system doesn't have passwords. It doesn't have a shell. It doesn't have user accounts. Basically took a portion of this space that you typically have with an OS and just excised it, which means we took that attack surface out of the equation. And of course, authentication. So we're doing mutual author certificate-based authentication. And we have our own authorization mechanism that's rooted in Pluton to give permissions to access to hardware resources like peripherals. So this is basic for those who focus in the OS space and desktop or server operating systems. But having an address space virtualization means application code just gets written once, compiled for different platforms, and runs. This is not something you typically have in an MCU. With a physical addressing, you're typically rewriting and porting your application to every single MCU platform that you port. So it's a much slower process for innovation. Obviously, source portability. We have a Linux kernel. We're focused on OSS. Most libraries, we have to support a large swath of the POSIX standards. So you can take common POSIX libraries out there and bring them to the platform. And with an A7 compared to something like an M4, you have a lot more headroom for the future for bringing new products to market through this through software update. So what are these firewalls? When I say the term firewall, I don't mean a network firewall where you have a whitelist and you're looking in software, for example, a table of IP addresses you're looking for. What I mean is that these firewalls are like a mapping. And this mapping is done in registers. And when you can map a peripheral to a core, so in this example we have multiple cores, the firewall guarantees that if another core tries to access that peripheral over the bus, that access is simply denied. It's just a no-op. So being able to program those firewalls and have them enforced in silicon and having a deny by default strategy means that you're guarding against cross-core attacks and cross-core vulnerabilities. So this applies to every resource in the system. RAM, network, flash, and every single peripheral flows through this mapping in silicon. So this means, if you're on one of the cores and a hacker attacks it and they have access to UART and they want to hop over and access a SPY or access some of the SRAM attached to the A7, it's simply not possible. Now, one of the interesting properties here is that we talk about a lot of these silicon defenses as sticky. And what does that mean? It means once you program this mapping, it cannot be reset. So even if until the entire chip goes through its reset process. So even if the code that programs the firewall is exploited or has a privilege escalation, an attacker cannot reset the firewall and reprogram it for access to resources it didn't originally have. Having that, you can think of as a write once setting. Finally, we have an MCU. We have a traditional MCU on these cross-core MCUs. It's where you do real-time computation. Real-time access is basically bare metal execution with a traditional RTOS. Because of that compartmentalization in silicon, we prevent that software from basically running amok other than the sandbox we provided it. So basically, you can run whatever you want there. A lot of manufacturers have their existing RTOS that they want to run, and they're free to deploy it and run it. We just treat it like an application. So we have a lot of silicon partners that have made announcements of supporting these chips. We're the first chips from MediaTek. It's called the MT3620. It's available in market now. We're going to see a lot more chips coming to market in this space over the next couple of years. So let's talk a little bit about the operating system. At the bottom, we're running an ARM processor. We're running in trust zones. In trust zone parlance, in secure world, we have a security monitor that protects access to resources. All those silicon countermeasures I talked about are all programmed from secure world. They can't be set from normal world. We have our custom Linux kernel. These on-chip, we're calling cloud services for authentication and connectivity. And then you have our application, we call them containers or sandboxes. Don't think about a Docker container. In the space we're talking about with a couple megs of RAM, a typical application is maybe 80 kilobytes. So we're talking about a sandbox that's reduced the surface area for execution. So a little more detail here. So as we mentioned earlier, in this curated user environment, there's no passwords, no shell, no user accounts. Basically, the application has its own manifest format. The manifest is part of the application package that's signed by Microsoft. We can parse that manifest, determine the exact resources the application is requesting, and guarantee that only those resources are accessed. Of course, we use things like TLS to implement mutual authentication. Those are run inside the operating system in normal world. Our Linux kernel has its own Linux security module that protects resource acquisition and manages access to Pluton services like our random number generator. And the security monitor, in addition to granting access to hardware resources by programming all those silicon countermeasures, also implements technologies like erasure coding to guarantee against runtime corruption on flash. So that's the OS. Let's jump to the security service. What are we getting out of the security service? How do we actually broker trust? Well, we use the security service to connect all our devices, and we send our failure reporting through it so we can do analytics and look for attacks out in the wild. We also use the security service to push updates back down to devices. And Azure Sphere device updates can't be turned off. It's part of the agreement that device manufacturers accept that we're always allowed to take an update and push it out to the device. So what are we getting from this attestation? So remote attestation allows you to check not only the device is running genuine software, but it's running up-to-date software. So the way we're leveraging attestation is that an up-to-date device is issued a very short-lived cert. So think about a cert that only lives a day. That cert then can be presented to any service, whether it's AWS or Azure. And if you can verify the cert chain, effectively Microsoft is vouching for the health of the device for the moment in time when attestation was completed. If a device is out of date, it doesn't get the cert. It actually gets something called a quarantine cert that can only be used to connect to our update service, and we can force that update to occur. So this allows us to prevent, basically allows us to take the security service and scale out beyond Microsoft services by using a certificate, which is a really common format that can be understood and parsed. So, Course Views Visual Studio. For development, you might be surprised that a lot of times in the MCU space, modern development tools aren't very common. So bringing a Visual Studio to market, and I think there's a demo, I think tomorrow, so you guys can play with the device and see how easy this is. Taking the development kit, connecting up to Azure and sending telemetry takes about 10 minutes. So I'm running out of time, so I'm going to conclude. The other thing I want to talk about, we might not normally talk about in this space, is we talk a lot about subscriptions right now. Subscriptions is a big way a lot of companies do business. We didn't want to do that when it came to securing your device. We didn't want you to have to think month to month, is this device worth securing or not? So when the chip is sold, it comes with a license. The license guarantees the security service is going to run basically for 10 years. We guarantee updates. We'll manage and service the device. So that cost, I think the public price we've announced is less than $10 for 10 years, so including the chip. So we're hoping to basically take some of the security service and push it down market into the MCU space with a lot of the features we're talking about in Pluton. The other thing is that it's open. So we're licensing the Pluton subsystem for free to any silicon manufacturer that wants to implement a Sphere chip. We are, of course, it's Linux kernel GPL, so that's open and available for people to contribute to. And it works with any cloud. So because the way the security service works, if you're hosting all of your services in AWS or Google or Azure, you can leverage the security service for the security of the device and work with any service that's out there. So that is the 10,000 foot view of Azure Sphere, and I'm happy to take any questions.
You mentioned, thanks for the talk. You mentioned the issue of, it seems like updates are critical,
yeah.
And there seems to be a tension between what you allow to be updated and what may not be updated. You mentioned the firewall can't be updated, and yet other things can be updated. Obviously, if the firewall has a vulnerability in it, you'd want to update it. Could you say a little bit about how you resolve, what's the philosophy and how you resolve the tension to ensure that updates can't be abused and yet they will occur when needed?
Yeah, great question. Basically anything in software can be updated. So the real tension is what do we push into silicon, and is the functionality pushed into silicon either simple enough that we can have confidence it's correct? So a bug in the firewall in silicon would be not updatable, right? That would be a core vulnerability in the chip that we effectively have to recall the chips and replace them. Or we try to use things like formal verification. So portions of Pluton have been formally verified to ensure that, for example, the cryptographic algorithms are correct. If it's in software, we're going to update it. We're going to ship updates out to it. So we try to draw that line in terms of what we put into silicon and what we keep in software, determine what's updatable. But it's tough because if you ship a bug in, putting these cryptographic algorithms in silicon means they're going to be more secure, but it also means if there's a bug, you're going to have to actually go out and replace the chip.
Great. Hello. Yes, my name is Daniel. Sounds like this may incorporate the use of like a mini hardware security module, and if so, has it been submitted for NIST validation? And if so, what FIPS level are we shooting for it?
Great. I don't have all the details. So we're FIPS compliant, and I think the team working because I didn't mention this. Pluton comes from a few decades of experience with Microsoft hardware. So this is internal silicon. This isn't brand new. It's internal silicon that's been defending other products and protecting other products in your ecosystem that we've kind of simplified a bit and brought down into the MCU space. So we've gone through internally FIPS compliance. We have not gone through formal FIPS certification, but we get asked about that a lot, and I think that's going to be the next step. And I guess that's one thing I forgot to mention is that you mentioned HSM. Pluton does generate its own key pairs internally in silicon as well. So we have, there's some of these chips where you blow fuses and you take keys, you do them in HSM, you send them over wire. We even feel like that's insecure. So the keys are never accessed by software. Even the most trusted piece of software on the device can never see the private key. It's all generated in silicon and Boolean fuses. So that's a good question. Thank you.
Hi, Sibin Mohan from UIUC. You talked about, your motivation for this originally, you talked about MCUs, right? So is there any kind of, are there any kind of real-time properties that can be guaranteed or real-time priorities in the Linux OS that they've designed for this, or can we add it in later?
I think you could look at adding soft real time, but it's one of the reasons why we have that extra M4 core, that M core that was on that diagram that's kind of firewalled off, is that if you, basically the M core is bare metal execution. So you can load in RTOS for your RTOS, some other RTOS on there, and have full control over the core. Microsoft doesn't interfere with it. So if you needed to do microsecond timing or something like that, you could do it there. So Linux is, so because of all the connectivity operations and update and other pieces that go on in the Linux kernel, it's not really the place you want to do real-time execution. Yeah.
Does it have control over the MMU and memory management as well, the M-core?
The M-core doesn't have MMU. It has an MPU, so but it's given us some segments in which to execute, and then within that space, it's free to do whatever it wants. So it's free to take that piece of RAM that it's given and treat it however it likes. Other questions? All right, great, thanks. If there are other questions, please reach out to me. I'd love to talk about it. Thank you.
Hello, I'm Adam Chapala, and I'm going to be talking about some of our experiences applying formal methods to systems and some ideas for, now that formal methods are relatively practical for this kind of stuff, what does that mean about how we should change the way that we design our systems and take advantage of some of the structuring principles that formal methods allow? So let me start out by talking about maybe the standard story people have in their heads about how we're going to use formal methods. We're building systems. We somehow gather requirements for what those systems should do. We have designs, and then we write some code, and we iterate through applying quality assurance methods like testing and debugging and code review, and we do that enough, and we become sufficiently confident that we can release something and let people use it and not be too worried about serious security problems. So the standard story of formal methods is that we have it as an alternative kind of quality control that we apply without really changing the parts of the implementation approach that would normally be used, but we're going to do some extra work to prove that the system really does what it's supposed to do. And in particular, especially for my own work, what I'm talking about here is mechanized end-to-end proofs of functional correctness. So let me take a few slides to briefly summarize what I mean by those words, and then I'll get into some more applications of the approach. So when I say mechanized proofs, I mean we use a theorem prover software package called a proof assistant. The one my group uses is called COC. And what this means is you can take the actual source code of your real system and write a formal specification for it as source code in another language, and finally write a proof as source code in yet another language that establishes that your system really meets the specification. We're going to feed all of these three into the proof checking software package, and it will automatically validate that the proof actually establishes the specification that you have in mind. And when I talk about functional correctness, I mean we're not just going to, for instance, prove that the system never crashes. We're going to write down a rather specific concept of correctness. For instance, if all the inputs up to this point were the following, then the output had better be this. And finally, when I talk about end-to-end proofs, I mean we have halfway realistic systems that are naturally broken up into layers, and the layers all have their own specifications, and we can prove each layer individually, but then we take the time to plug all these results together and get an end-to-end guarantee that only needs to talk about sort of the top and bottom APIs of a stack like this. And many of the internal details drop out of the trusted computing base. So these kinds of ideas can influence the ways that we address classic trade-offs in system design, like the one between performance and maintainability, where usually we worry that as we improve the performance of a system, the code gets harder to understand, but it's worth it given all the use that we expect our systems to see. So one question that we might have is this pattern fundamental, where today we expect building a realistic high-performance system involves writing a lot of intricate low-level code where it's very easy to make mistakes that jeopardize the correctness or the security of a system? So let me try to convince you that we can use formal methods to actually change this assumption for building realistic systems. And I'll do that with to start out with a concrete example that we've already explored at MIT. So one area which was mentioned as just part of the story in the last talk is cryptographic primitives, and in particular elliptic curve cryptography is one of the most widely used approaches, for instance, for initiating an HTTPS connection. And here's some C code written by one of the experts on this kind of stuff for the elliptic curve that is generally viewed as the easiest one to implement efficiently. And I think this is code for taking a big number that's too big to fit in one register of hardware and squaring it modulo some large prime number. And it is moderately intricate, and it's repetitive enough that if you try to audit this, you might easily lull yourself into a false sense of security and believe everything looks okay. And this is just one part of a larger piece of code, which historically this kind of thing has all been written by hand. But it would be nice to know this code is correct, and there are a few competing approaches to doing that. One of them is to find a student or an intern who's willing to read through all these lines of code and write lots of invariants and convince an SMT solver that this is correct. And that's a wonderful time-honored technique that I won't try to trash talk too much. But what we could do instead is wonder, do we really need to write code like this to get high-performance crypto? Maybe it's an opportunity to notice building formal proofs of things is hard. It pushes us towards simplifying system implementations, which is an independently useful thing. Maybe there's a better way to write this where we'll get a proof and we won't have to look at code like this. So just to motivate a little bit more about why this is an interesting domain, the standard advice is don't write your own crypto code, and probably most developers try to follow this advice most of the time. We have a relatively small number of libraries that implement the most important cryptographic routines. But there's a moderately large space out there of different cryptographic algorithms that matter. And then there are parameters for those algorithms. One important example is a large prime number that you use as the modulus for arithmetic. And then there's a small to medium-ish set of interestingly different hardware architectures that we want to run this code on. When I was first learning about this area, I was really surprised to hear that for every element of this three-way cross product, the state of practice is to rewrite all the code from scratch, sometimes in assembly, to get the best performance. So there really isn't, or there hadn't been very good abstraction in the way that this kind of code is developed and maintained. And that means there are a lot of opportunities for making mistakes where we get incorrect cryptographic primitives that can wreck your security guarantees. So we wanted to go at this in the so-called correct by construction way. It'll be sort of a way of writing the code so at every point, all the code you have is guaranteed to be computing the correct answer. And there's a long history of this kind of formal reasoning in cryptography, where we typically start with a property like, I have a digital signature scheme. No one can forge signatures if they don't know the right secrets. And then we can apply the idea of protocol verification to show that some mathematical algorithm provides that guarantee subject to standard assumptions. And then we could do, for instance, implementation synthesis to come up with low-level fast code that provably implements that algorithm. I think the next talk in this session will talk about the other direction, implementation verification, where you have the code already and then you're going to prove that it implements the algorithm. But let me talk about the downward direction, the way I've drawn this here. Implementation synthesis is what I'll be focusing on in this project. So to give an idea of how we can, in a principled way, derive the code that we want to run instead of just starting with a pile of C code or assembly, we'll start out with mathematical algorithms, which in this domain of elliptic curves are all about two-dimensional geometry. And then typically one substitutes in a less obvious but more efficient implementation of points, which sort of counterintuitively adds more coordinates to make things faster because we can run fewer expensive instructions when we rearrange things this way. And so this first step is just a classic data structure correctness proof in the sense of abstract data types and abstraction relations and all that stuff. So we write down an abstraction relation between these two versions and prove that it's respected by the code. Then we have to implement the individual coordinates of these points, which are all by themselves pretty hard to get to run quickly because every coordinate is way too large to fit in the registers that commodity hardware provides. So we have to think about division of numbers into multiple digits. And so we prove kind of big num arithmetic in this style to connect that part. And then finally, an aspect that I won't have time to talk about in too much detail, we have a verified compiler at the end that takes the functional programs that are coming out of this process that work with infinite precision integers and infers bit widths for all temporary variables and does other compiler optimization things. And then out pops sort of idiomatic C code with particular types for all the variables that are being used. The important thing is each of those arrows on the right side is carrying a proof, and they're all snapped together in a common framework. So we get that the low-level code is truly implementing the mathematical algorithm that we started with. And this whole pipeline runs automatically. It's not a new manual effort to consider a new space. I showed you 3 clouds. When you change up one of the second 2 clouds, this is automatic. When you have a new algorithm, that's new work. So our project is called Fiat Cryptography. It takes place within the context of a larger multi-university project called Science of Deep Specifications, which paid for this lovely logo, which is a reference to the Spy versus Spy comics for anyone who is familiar with those. And I've listed down here my students who've worked on this project. This is basically a platform for correct by construction generation of elliptic curve cryptography implementations, and we hope later other kinds of cryptography. So what we basically do is we're going to think about the arithmetic that goes into these algorithms at a high level. We're going to do some functional programming of the kind that you might even assign in a freshman programming class. We're going to represent big numbers as lists of pairs of numbers. Every pair has a compile time part and a runtime part. The compile time part is the weight of that digit. It's like how many bits to shift it by. And the runtime part is the actual digit value. We're not going to be very specific about which weights are allowed, whether we can have duplicate weights or anything like that. We just have lists of pairs of numbers, and we can write down implementations of classic operations like multiplication. But that one works by just taking all the cross products of the elements of 2 lists. And we can just write that as a functional program that uses famous higher order functions like flat map and map. And it's a very small amount of code. And we can write lemmas that we prove in the Koch theorem prover that shows that this multiplication operation is related to the normal multiplication operator in the appropriate way. Then we can take ingredients like that and put them together into higher level operations. So this is one that is going to take in 2 big numbers, A and B, that follow a particular digit representation with n digits in this case. This function is actually generic in the number n using polymorphism. And then we convert each of those fixed representations into our flexible internal representation. We do the multiplication. We run a mod operation, which is by convention called reduce here. And then we convert back out of the flexible representation into the fixed network format. So this is a really nice from a software engineering standpoint. This code is so much easier to understand than the C code that I showed before. But if we just say take this and treat it like OCaml code or Haskell code and compile it in the normal way, it's like 100 or more times slower than that C code that I showed. So we need to do something about that. And the approach we're going to take is a classic idea in compilers called partial evaluation. So we have, for instance, our multiply operation. It's parameterized on a static part, information on the digit representation of numbers, which could be different for different elliptic curves. And then we have the actual digit values. So first, we'll specialize this function to a particular set of digit bit widths. Now all it takes in are the digits themselves. And then we will reduce and simplify algebraically that program until all the overhead of the genericity is gone, and we have a lean specialized multiply routine. And then we'll actually feed this into the verified compiler I talked about, which will infer bit widths and do the other things you need to get C code from the functional programming view that we started with. So how does this actually pay off for performance? So I should mention, each of these arrows here is a built-in operation of our chosen theorem prover Koch, so this is all very straightforward to do. Specialization is just partially applying a curried function to some of its arguments, and the reduce stage is just calling a built-in reducer that is one of the standard building blocks of proof of program correctness. So that's a very natural process. So we get out C code that looks a lot like the code I showed at the beginning, at least at the abstract syntax level. It's not as nice to read directly in the concrete characters that we output. And if we compare performance on curve 25519, which is the, for instance, Google wants to talk this curve to you if you try to connect to their main website. If your browser supports it, it'll use this one. And here's some examples of how many CPU cycles are needed for one of the top-level elliptic curve operations. I forget which one. And we can see there's our code up at the top there. We generate both 64-bit and 32-bit versions. So these benchmark results are on a 64-bit machine, so the 32-bit results aren't super interesting for performance. And we're very close to the best known assembly code for this elliptic curve. And in fact, we are now, as far as I know, generating the fastest known C code for essentially every elliptic curve with one automatic pipeline that generates proofs. And to demonstrate that, we scraped information on elliptic curves online and tried to compute the set of all the prime numbers that anyone associates with this field, so we could automatically generate implementations for modular arithmetic for all those primes. And we did it for both a 64-bit desktop machine with an x86 processor and a 32-bit ARM machine, which is actually an Android phone. And we compare against the previous highest performance generic implementation of this stuff, which is the GNU multi-precision library, which has multiple variants, one of which actually is appropriate for secure crypto-style applications where you don't leak information about inputs to your arithmetic through timing. But we also compared against a version that does leak information through timing, which should only make it harder for us to show performance improvement. And still, over the space of all these primes that we spidered off the internet, we're seeing typically a performance improvement in the range of 2x to 10x, and we have formal proofs of all these implementations, which the GNU multi-precision library doesn't have. And finally, we managed to convince the team at Google that manages the boring SSL library, which is it started out as heavily inspired by the OpenSSL library, but has diverged a lot since then, to adopt our approach to replace their grungy handwritten code for elliptic curve arithmetic. So the two most commonly used elliptic curves are curve 25519 and P256, and our code is in there now for both of those with distinct 64-bit and 32-bit versions. And there's a student doing an internship as we speak at Google who will hopefully have P384, the third most frequently used elliptic curve, done in the next month or so. And so this library is used in Chrome, it's used in Android, it's used on Google servers. And so now about half of all HTTPS connections from browsers use our formally generated implementations of elliptic curve operations. So I started out posing this question: do we really need to spend our time writing intricate low-level code to get performance in the systems that we're building? And if we're talking about formal methods, it's probably not a surprise that we can, to some extent, get rid of that bug-prone quality, even if we keep writing the same kinds of code as before. But hopefully I've also showed how we can remove the need to write low-level code and do more of our thinking in a nice high-level way with more of the nice software engineering properties that we prefer to have. Here's a related question. Whenever we add new abstractions to a system, we worry that there will be some performance cost for those abstractions, even if it makes the system nicer to think about. If we do adopt these kinds of end-to-end formal methods, there could be ways to lower the costs of adding abstraction to a system that we might not think about if we have to stick to traditional implementations. So let me talk about one way to think about how we could apply this idea in general. I think that the last talk was a great example of a classic approach to security and isolation in a system by imposing various runtime mechanisms to contain compartments and limit what could happen to different parts of a system. I think of a lot of different examples, from processors to operating systems to database systems, as having their missions in life are to provide a kind of high-level imaginary view of how a bunch of parts of a system run and share resources, where we can imagine there are these impenetrable walls between the different subparts of a world like this. And every one of the parts gets to be written in a nice high-level language. It uses nice APIs. We can pretend there are dedicated processing resources, dedicated storage, and so on for each one of these blocks. And many traditional deployed systems today literally realize this picture in the way hardware and software are set up. But in general, what we're trying to do here is come up with a real optimized system that, in some sense, can be having a dream and imagining it lives in that nice world, but there's a lot more resource sharing to improve performance in various ways. And we might call this top view of things a virtual machine, in maybe a kind of older sense of the phrase, which is just a nice abstract view of an executing system that doesn't have to get into the details of how we do resource sharing. Or we could just call it a specification, which is already a common idea in formal methods, and think about how we can use compile time reasoning to show that a system truly implements this abstraction without leaving any runtime residue of the approach that forces us to keep paying a performance cost each time we use the mechanism that we develop. So one direction that I'm interested in pushing on in the near future is to try to take this all the way and move all of our reasoning about isolation to compile time and get good performance, get good abstractions without having to make compromises there. So the idea is I wanted to think of a stack of systems components as essentially a platform for efficient execution of simple functional programs where we build up abstractions that successfully show how to implement the high-level features that we're relying on. I want the starting specifications we work with to be so simple that we can more or less just have a few people read them and we'll catch the major issues. The code will be so short that that's feasible. I want to try applying a proof-carrying code approach where we just say, if you want to run your code on my system, you need to give me a proof of full functional correctness, or I'm not going to accept it. And I think this is getting to be feasible for both software and digital hardware. And this should be doable in an end-to-end way where we're going to take all the proofs that we require be provided for all the components installed on the system and snap them all together so that we get a very small TCB that contains just our proof checker as well as the semantics of sort of the top and bottom level APIs of the system, where the bottom is ideally a hardware description language and the top is just the nice high-level functional version of our applications and the system API view that they see. And if we do this right, each of those top and bottom levels should be on the order of 1,000 lines of code and very doable to audit and catch major issues in. And we should be able to, by using this proof approach, avoid all runtime isolation mechanisms and push all of our reasoning about that into proofs. So here's an example of a stack of pieces that could head in that direction. So I want to start with the top level view of the system is nice functional programs that we could view as the specification, and they would use design patterns like object capabilities so that just by construction we achieve proper least privilege and we control the information flow graph within parts of a system. We achieve access control just using pointers in a type-safe language. And then we can rely on a compiler that's going to produce C-like code from that point that does things like static analysis to infer object lifetimes, to insert manual memory management code so we won't need anything like a garbage collector. Then our systems level programming language wouldn't need to have a type system, because if we're already committing to proving everything functionally correct, then a type system is just an approximation of functional correctness. So we can leave that out and expose a view of memory as an array of bytes directly, but with structured control flow and functions and other good stuff like that on top of it. The compiler for that language will do things like worst case running time analysis, tell us how long a function might take to run. This might depend on some annotations that the programmer needs to provide and maybe prove some things about. But then once we've done that, we can output machine code, which is prepared to run on machines in the microcontroller class that was one of the parts of the diagram the last talk showed, where we don't have virtual memory or other address space protection. We don't have interrupts. We just have a machine that knows how to run machine code functions when you ask it to. And so then what does the processor do? It keeps receiving I/O events from the world, and for each one, it knows which function to call in the pile of machine code that we've produced, and that function just runs to the end and decides what to do next, including signaling any response output events that should happen. And it's safe to avoid using interrupts or anything like that here because we did worst-case execution time analysis on all the code, and we don't depend on virtual memory to isolate the different parts of the system because that was all present in the original functional code through object capability system and other such patterns and preserved through semantic guarantees about all the levels bringing us down to this point. One thing that's kind of hard about good worst-case execution time analysis of realistic code is predicting the cost of memory operations given complex cache systems. So one other idea that we're thinking about is taking the high-level view we have of code to preserve down through this whole stack proved accurate characterizations of which objects in memory each function is going to need so that the memory system and the cache coherence protocol can move into place in the cache of whichever processor gets picked to run a function, guaranteed all the objects it's going to need so that when we actually run the code, we know exactly how long it's going to take, or we can at least get a much more accurate bound than before. So that's the idea there. And to summarize, I think it's worth exploring how some of the challenges that we're used to seeing as fundamental in the design of systems software can really be rearranged by committing to functional correctness proofs for all parts of a system. And this technology has really advanced a lot. I think in the next 10 years or so, this will be mainstream. And I think it's interesting to consider what domains there are out there where if we wanted to re-implement all the complete software stack from scratch, this would be pretty feasible. And I think there are more cases of that than we'd think from the usual conversations about this sort of stuff. Thanks. Questions?
It's very impressive. Could you say a bit about how you would have caught the problems of interference between speculative execution and caching in this picture? And more generally, our processor abstractions have the property that there are a lot of details we don't know about. And in a sense, abstractions are bad for security because they hide from the implementer properties that the attacker takes advantage of. So how does that fit into this picture that's strongly based on abstractions?
So let me start with the second question, or maybe try to clarify the intent of it. If you're talking about abstraction through closed hardware designs from manufacturers out there today, then that doesn't fit so well into our picture. But if you think about open source hardware designs like are coming up in the context of the RISC-V instruction set, then that fits completely well into this picture, and we're doing some work in that area ourselves, where you can assign a semantics to the hardware description language that includes timing of all interactions with the outside world, and you can formulate what it means for timing to be independent of secret inputs coming in on certain wires. And then if you manage to prove that theorem, then you really have avoided Spectre and Meltdown kind of attacks. But there is a challenge there that I think the architecture community doesn't quite know yet what the actual changes to the workings of processors are to avoid those issues while keeping performance. So we'll just try to be ready with general proof tools for whenever those mechanisms are known.
So I've got a question. So,
yeah.
Related to timing, how much when people write these functional correctness specifications, how much do you expect people to say about timing? Like if they say I'm going to send 5 messages to somebody, do they have to say exactly when they're going to send those messages so that they don't leak any bits through the timing of the messages?
Right. So one approach is to require high-level functional specifications that for each operation you can run, the functional program needs to compute the running time that it expects to have in the real world. And that could be kind of an opaque function that you don't know what it is, but you know it's well-defined and deterministic. So it's hard to see how to avoid heading in that direction to really avoid all the information leaks, but this is pretty speculative right now.
Thanks. One question is about observing side channels other than timing. So, for example, power side channels or radio emissions. What aspects of your work do you think translate well from timing analysis to other analysis, and what aspects don't?
Yeah, so those other side channels I'm really not very well informed about, but if someone who could come up with some security condition that applies to RTL designs, then we could probably incorporate that in this framework. I'm not informed enough to know what that kind of condition might look like.
So as you were presenting the crypto work, the voice in my back of my head was saying, oh yes, but crypto code has a nice clean functional spec and it's all self-contained. It doesn't have to deal with memory models and interrupts and all these things. And then we get to the end of your talk and it seems like your answer to that problem is, we'll make it go away, right? That's a great clean slate design, but do you have any thoughts about how we get from here to there incrementally? Because that sounds like a hard change to make. The crypto stuff is easy to deploy because it plugs into the existing system and it observably makes it better. But I don't see how you could incrementally deploy something like this. Have you thought about that?
So I think I'm not suggesting incremental deployment in that sense, but just building some cool boxes of the kind we heard about in the last talk using this framework, which then talks to the rest of the world through standard protocols and interfaces.
Any other questions? Let's go ahead and thank Adam.
Thanks, Chris. So this is a talk about Project Everest, which is a joint effort among several Microsoft labs, as well as INRIA and Carnegie Mellon. And it's a project that we've had going for a couple of years now that's aiming to build and deploy verified components in the HTTPS ecosystem. So I think you know what HTTPS is. Even if you don't, you use it, I'm pretty sure, every day. Essentially, when you connect on the web to any secure website, whether it's a bank or your email, you negotiate a secure channel using a protocol, a cryptographic protocol that underlies HTTPS. On the surface, the most common usage is through this web protocol, but within HTTPS is actually quite a complex ecosystem. There's at the heart of it is a protocol called TLS, Transport Layer Security, beneath which lie several crypto algorithms, and alongside it are things like the public key infrastructure, ultimately talking to the network through TCP. Above it are clients and servers that incorporate this suite of protocols. The trouble with HTTPS is that although you should still use it and it's significantly better than not using any protection at all, the protocols in this space and the algorithms in this space have been hit by attacks and corresponding fixes for 20 years or more. Maybe the one that's got the most attention is this Heartbleed bug, which in a way is a very boring bug. Heartbleed was essentially exploiting a buffer overrun, a memory safety vulnerability to compromise TLS, implementations of TLS. But there have been other kinds of bugs too that are independent of implementations. There have been design flaws in the protocols, all the mainstream implementations have been subject to these flaws. OpenSSL is the most widely used implementation, but Microsoft's S-channel is also very widely used. There's NSS from Mozilla. There are others, Boring SSL, things that have forked from OpenSSL. All of them have been attacked and get repeatedly patched. So in 2016, we started a project that had a 5-year scope, so we're about halfway through it. And we had a few goals. Our first goal was to build a verified implementation of the components in HTTPS. And our goal is to actually build these components in a form where they are low level and are efficient enough to be deployed as is inside the existing software ecosystem. In doing so, we are building and improving verification tools that have been developed at MSR. F-star is a programming language that it's a proof assistant in the spirit of something like Coq that Adam mentioned, but using an automated theorem prover called Z3 that's also been developed at Microsoft. In pursuing Project Everest and building these verified components, we also aim to produce more trustworthy, usable verification tools, and to grow expertise in building this kind of verified software at this kind of scale. And finally, we strongly believe that this kind of security work has to be done in the open, so everything that we do is open source, including the tools. F-star is open source, and all the verified software that we build. We're a large team of people who work on this at several MSR labs, so Redmond, Cambridge, and India, several of whom are in the room. There's Chris and Tahina and Jonathan, at least, that I see, who work on Everest. So feel free to come find us and ask us questions about this. There's aside from the MSR labs, we have collaborators at INRIA in Paris, who we work with. There's an MSR INRIA joint center at Paris, and we work with them through this arrangement. And we have collaborators at CMU and at the University of Edinburgh, and a long list of interns, visitors, and so on. And we're very open to collaboration, so if you're interested in this kind of stuff and would like to work with us, get in touch. And so here's where we are at sort of 2.5 years. We have verified implementations of most of the key cipher suites that are used in TLS. We've, for the moment, not looked so much at the public key infrastructure, but have instead been looking at a protocol called QUIC, which is a new development in this ecosystem. So QUIC is a new networking protocol that has been is undergoing a standardization process at the IETF, driven initially by Google, and it's trying to do TLS over UDP in a kind of a new clean slate redesign. So we have deployments of our verified code in test deployments in 3 clients: the Edge browser, the curl library that lets you do command line. Curl is actually used in many tools, but it's one of its usages is just fetching pages from fetching web content. Nginx is a open source web server, and we have a test deployment in there. But aside from these test deployments, we have 2 main production scale deployments. So Windows is developing an implementation of QUIC called WinQuick, and WinQuick uses TLS, and Everest's TLS runs in WinQuick and is now part of the Windows development builds. We also, being open source, our code runs also outside Microsoft. So Mozilla's NSS library, which is used in Firefox and in other Mozilla tools, it runs Everest crypto, specifically the crypto algorithms, not yet the protocol stack. So, when talking about verification, there's always a question of like, well, what do you actually verify? And as a baseline for all this kind of work, we verify safety. So without memory safety, you can't really get very far in proving anything further. That's the baseline level of abstraction that you need to prove. So we prove safety for all our code. And then depending on the component that we are verifying, we pick properties that we think are the most suitable for those components. So usually this means at least functional correctness. But for certain components, we will also prove things like cryptographic security, meaning that we bound the probability that an attacker can break a certain crypto construction. Despite all our proofs, you may ask, will Everest be perfectly secure? And the answer to this is no. all this kind of verification work is based on a set of assumptions, both with respect to the specifications that you write. So, if you're skeptical about Everest or any verification project for that matter, you need to study the specifications that are actually proven about the code and convince yourself that the specs actually mean what you think they mean. Specs are written with respect to a model, and our models try to be detailed and cover all classes of known attacks, but there may be new classes of attacks that we are not aware of that may make our models inadequate. Also, our verification tool chain places trust in a number of components, including F-star, the Z3 theorem prover that we use on C compilers, and so on. And those are part of our trusted computing base. Despite these limitations, the general methodology of using computer-aided verification has some clear advantages. Verification is automated. It may take several hours, but you make a change, and you want to know if your change was breaking a system invariant. Well, the verification system is going to tell you as part of a continuous integration system. The way in which you can get a proof to work at this scale is by breaking it up into components. And so verification is modular and compositional, meaning that you can take a component, say, a particular crypto construction that we use inside TLS and also use it in some other component, which is, for instance, our usage of TLS in Quick is a great example of this. TLS was intended for use initially over TCP, but the same crypto protocol can also be used in a different setting like Quick. Right. So the programming and verification tools that we use at the source level is a programming language called F-star. F-star makes use of Z3 to prove verification conditions that arise from as you try to write your program. So after you write your F-star program and verify it, you can compile it either to OCaml or in a tool that we've developed as part of Everest. You can extract your F-star code to C and then compile it using a C compiler and link it with the rest of your system. So let me do a small demo of this. Is that big enough in the back? Ish, okay. This is F-star running in Emacs, and F-star program, its syntax superficially looks a bit like functional languages like OCaml or F#. But within this framework, you can encode other DSLs. So I'm showing you here a DSL that we have in F-star for writing C-like programs. And this demo is a very simple example that's showing how you may copy the contents of one array to another. Copy from the source array to the dest array. And the way in which you do this copy is really simple. It's a recursive function that assigns the current byte of source to dest and then recurses on increasing the counter by 1. Now, when you try to write such a program, you're forced in F-star to prove various basic properties about it. So you see these comments that I have here that say that at various points in this code, F-star will force you to prove temporal safety, for instance, meaning that you cannot access a memory location unless you prove that the memory location is currently live. Or when you do an integer operation, you need to prove that there's no integer overflow. So having written this code, you can ask F-star to check it, and it'll say, in this case, says yes. But if I forget a precondition, for instance, I try to use the source array without knowing that the source array is live, and I ask F-star to verify it, it'll complain, pointing at a location here that says, well, at that index, this says live. You couldn't prove that the buffer that you were accessing was live at that point. So this first attempt here is just proving that copy is safe to run. It doesn't prove anything about what copy actually accomplishes. So this bit of the spec here is an ensures clause, which says at the end of running this code, there's something that you can assume is true about the state of the program. And in this case, the ensures clause is just true. So you don't get anything, you don't get any functional correctness property out of this version of copy. But here's another version of copy where It's the same code as I showed you before, but it's now augmented with a spec that tells you that after you run copy, in the final memory H1 that results after running this program, the source and the destination buffers are equal, which is what you might expect from doing copy. So F-star likes that, agrees with this specification. So having done this, you can then, having verified your program, you can compile your program to C. And here, I did this just a little while ago. So this is an extraction of the previous program to C. And notice that when you extract to C, you just get C code that you would expect with all the specifications erased and with no remaining runtime checks or anything. All the verification is static. So this style of verification generally imposes no additional runtime performance overhead. All right, so that's a sublanguage that I showed you in F-star for programming at the C level of abstraction. But to get performant code, especially in some of these crypto applications, you need to go beyond C. And so we have another DSL called Veil, which is a DSL embedded in F-star for programming at the assembly level, building verified assembly programs. With these tools, we aim to build TLS and protocols like it. And for TLS, the main security goal that you're after is to show that TLS establishes a secure channel, meaning that you get a channel between the endpoints that is authentic, meaning that an adversary cannot inject forged data into the stream, and is confidential, meaning that an adversary cannot distinguish between the communication of random bytes and a secret on the stream. The TLS protocol has, through the years, been, its design has been vulnerable in many ways, but TLS 1.3 is a new version, the latest version of the protocol that is now a IETF proposed standard. In the process of us verifying TLS 1.3, we discovered many potential protocol flaws in earlier versions of the design and proposed, I think we have 6 proposals in the proposed standard that have been incorporated in the proposed standard that arose as a result of us doing our verification work. And the IETF has generally been, I think, quite receptive to this, at least in the TLS committee, has been receptive to this kind of formal work as well. The standard, for instance, cites both ours as well as several other formal models of TLS as a validation of the design of the protocol. So the way in which we model cryptographic security is, and prove it, is in the following manner. So you have a concrete implementation of TLS that's using a crypto provider, a crypto library that's implementing the actual algorithms. And you have an application program which may also represent the adversary interacting with TLS. And what we do is, our general proof methodology is to show that this concrete version of TLS is indistinguishable from an ideal version of TLS about which we can prove that it actually implements a secure channel. And the way we do that is by verifying the crypto library and then making use of a cryptographic hypothesis to say, to show that clients of this library are, these two clients of this library are indistinguishable except for a security parameter, a probability determined by a security parameter. Having done that, we can then prove the ideal version of TLS, information theoretically secure, with no more cryptography in the picture. And with that step of the proof complete, you can then show that an attacker cannot distinguish between concrete TLS and ideal TLS, except also for some probability epsilon. So that's our general proof methodology at the top level. In order to apply this methodology, there are various proof steps that become necessary along the way. So here's the structure of one simple workflow through TLS. So TLS is a socket-like API. You connect, you try to create a secure socket. That triggers the run of a TLS handshake that's going to negotiate secrets between, negotiate keys between the two endpoints, which then requires actually, sending some plain text bytes out on the wire. That's which will then get the TLS record layer subprotocol is going to add some padding to hide lengths. And then finally, at the very bottom, there's going to be the addition of a ciphertext and a MAC to protect the actual message that goes out. So at each level, we have various proof obligations. So at the very bottom, you need to prove that the crypto that you actually implement is functionally correct. And we actually also prove that it's resistant to a class of timing side channels. So as Adam alluded to, we have a library called Hackle*, that's a library implemented in the C-like subset of F*, where we have proofs of many crypto algorithms whose performance compares quite favorably with the best handwritten C. It's actually interesting. I hadn't seen Adam's most recent slide. It looks like their version of Curve is slightly faster than ours. But this version of Curve, is a 64-bit version of Curve, is significantly faster than, it's like 2x faster than a handwritten version of the same Curve in OpenSSL, which was a 32-bit version of of the Curve that was the only one that OpenSSL had until recently at the level of C. So using our verification technology, we were able to write 64-bit versions of the code and be confident that we got it right. And it's actually this code, code from this library, our crypto library in C, is the code that we have deployed in Firefox. So there's the elliptic curve 25519, but also some other algorithms, Cha-Cha-20 and Poly1305, are deployed from Hackle* in Firefox. That said, the code generated from Hackle is competitive with C, but the best implementations in assembly are still significantly faster. So using Veil, we have verified the assembly code in OpenSSL more or less as is. And as you'd expect, if we get performance that is competitive or identical to the OpenSSL code that we started from. At the level of data streams, we prove that a distributed invariant, that the reader of the reader end of the protocol reads from a prefix of the stream that the writer has sent so far. In order to send messages down the wire, we need to prove that our parsing and formatting code are correct. At the high level, the main invariant that we're after is that if the application sends a message M and it gets formatted, then encrypted and decrypted and then parsed, the receiver receives exactly the same message that was sent. The way we do this is rather than writing parsers and formatters by hand, which can be very tedious and error-prone, we start from a high-level description of the message formats from RFC text and synthesize via metaprogramming a low-level implementation in C of parsers and formatters for those message formats. So I'm running out of time. I should wrap up. So just to give you, I'll finish with some high-level perspective. So we're building verified components motivated primarily by HTTPS. But in doing this, our components that we produce are reusable in other contexts as well. So Quick is one such example that I mentioned briefly earlier. But some of the work that we're currently doing also involves using our crypto libraries to build things like verified authenticated data structures that are used in things like blockchains. Recently, there's some interest in using our crypto libraries to verify the correctness of and security of post-quantum crypto algorithms. Our verified parser and formatter generators, although we're using them in TLS, we also see that they have applications in other secure messaging scenarios, for instance, inside kernel or in communications between VM and kernel and so on. Another high-level perspective about Everest is that rather than trying to build a completely secure stack from the ground up, what we're after is sort of building verified islands of trust inside the existing software ecosystem. And we think there's value in doing that. In a way, verification is a lot about the blame game. If we deploy our code inside an existing operating system, Linux or Windows or whatever, the entire system is still vulnerable to bugs, but any such bug is going to be outside of our code. If a patch has to be shipped, it's not us that's going to be shipping a patch, someone else will. Now, finding these islands of trust in which verification can add value requires some careful thinking. And we think that standards-based cryptography and networking is a really good match for it. Partly because there's a very widely accepted common wisdom that you're supposed to leave crypto to experts and not try to roll your own. So there's an opportunity for a well-designed crypto library to be used, crypto library and protocol library to be used as a drop-in replacement for the existing code that's out there. And also, I think another thing that we're quite encouraged by is that the standards process at the IETF and elsewhere is increasingly receptive to this kind of formal spec and validation, partly because prior versions of these protocols have really been badly beaten up by a cycle of attacks and patches. So we think there's an opportunity there. So that's it. I'll leave you with that image. It's our goal of trying to build and deploy verified components in HTTPS.
Hi, Rebecca Wright, Rutgers University. Thanks for the talk. So you noted at some point that, of course, all of these proofs are dependent on the model and that there is always the potential for attacks outside of the model. In the practical usage here, do you have sort of a sense whether it's sort of inherently a cat and mouse game that will continue indefinitely, or whether there's sort of, in a practical sense, some kind of convergence to capturing most of the meaningful potential attacks?
I think at a certain level, there's, at a certain level, at a high-level spec about what the protocol is trying to achieve, I think we're reaching a sort of a convergence. But there's always the possibility of vulnerabilities at the lowest level that our models don't account for. So, for instance, we have proofs of resistance against a certain class of side channel attacks, where we didn't anticipate a Spectre and Meltdown either. So although we think our code is not, for the particular kind of code that we write, it's not vulnerable to these kinds of Spectre and Meltdown attacks, our proofs certainly don't account for this. Those kinds of scenarios may still occur in the future.
Any other questions? Okay, well, let's thank the speaker again and head for lunch.